Let us go back to our area. We have already studied several types of resistive sensors, and we told that we'll classify the sensors in that way: resistive sensor, inductive sensor, capacitive sensors initially, so that it is easier to see the signal conditioning circuits are almost the same, and it is easier to teach that. So after finishing of the resistive sensors, we will go for the inductive sensor. So inductive sensors, from this name itself, we can see that it is the variation of inductance. You know, the inductance is given of a coil is given as mu 0 mu r n square A divided by L. Possibly all the terminologies are known to you. Mu 0 is the permeability of free space, mu r is the relative permeability of the material, n is the number of turns, A is the cross-sectional area, and L is the length of the coil. We often express it in this way: is equal to n square divided by r, and this r we denote it as reluctance, which is very close to the term resistance. You can see it, it is equal to L divided by mu 0 mu r into A. In a similar way, that is rho L by A. Here, that is for the resistance. For the reluctance, we plate it that L reluctance is equal to L divided by mu 0 into mu r into A. So naturally, we can basically, the inductive type sensors are means that with the depending upon the input signal or the process variation are like this, we will be depending upon the process variation like this, we would be varying the inductance. So if we can measure the inductance, we can variation of inductance, we can get the idea about the input, the process parameter. So we can see the types of the different inductive sensors there. Number is that variable reluctance sensor. So you can see that if the reluctance changes by effectively changing the length of or area, or by introducing some air gap in it. So these things all we have studied in the first year magnetic circuit problem. We will recapitulate once again this one. That is called the variable reluctance type sensor. Next we have it is that, so we can look at it and say like this, for an example, this is a very common, here we had it, problems of Parker-Smith or other problems are like this, that there is an iron core and there is two iron cores and there is some air gap. If you vary the air gap, the inductance, reluctance will change, and as a result, the inductance will change. Second is that variation of mutual inductance. So variation of mutual inductance, we can say that, okay, I have a coil here, and on the top of it I have another coil. Say suppose this is another coil and this inner coil or maybe the outer coil moves in between, keeping the gap same, but moves in or out like this. So as a result, if we this coil 1 and this is coil 2, if we vary the distance, the mutual inductance between coil 1 and coil 2 will be changing. The mutual inductance between coil 1 and coil 2 would be changing, and in that way we can measure the distance also. So it's a variation of the mutual inductance. We'll see that LVDT is a common term and common, very popular type of displacement sensor. It is based on the variation of mutual inductance. Third one is the eddy current type sensors. Here it is almost the same. Except the outer one is what we call it a short circuited sleeve. Outer one is a short circuited sleeve. That means a copper ring or something like this, and which moves in these directions. So as it moves inside or outside, what will happen is that, and definitely we excite it by some AC excitation. So if we excite it by some AC excitation, what will happen? There would be some magnetic flux generated by the coil, and that will be linking the short circuited sleeve. That will again cause the eddy current in the path here. So what will happen effectively is that the presence of the short circuited sleeve, the presence of the short circuited sleeve or its movement, that means it's moving in or out or like this, ultimately cause the variation of the inductance. The inductance, self-inductance L will change because of this EADR. That is due to the eddy current effect. That means the magnetic flux generated, it cuts the short circuited copper sleeve or aluminum sleeve there, that is causing some eddy current, and that eddy current will again generate some flux which will interact with the main flux, and overall A will be the variation of the inductance. And the last one is called variable permeability type. What is meant by variable permeability type? We'll see that some of the materials, particularly nickel, and there are certain alloys, we'll come to it afterwards. This permeability changes with applications of strain or application of force there. That is called, so fourth one is the variation of mu r. Mu r with your force or strain or like this. So broadly speaking, these are the four types of inductive sensors which we can have it. Often there are some variants there, but we will find that the inductive sensors are useful in many of the cases, but often sometimes they are a little bit bulky. And the major disadvantage is that they cannot be integrated in an integrated circuit, while for the capacitive or resistive sensors, they can be integrated easily there. These are the few problems, but this inductive type sensors, though a little bit heavy sometimes, it is often very popular and reliable and rugged. So I will just start with the variable reluctance type. With the variable reluctance type transducers, which we have had described. So basically, this winding, this diagram, I am keeping it. Is it too small? I don't think. This one you can. So what is happening is that here is the inductance and here is the gap is coming there. So we have got certain A there, that is the L is equal to total length of the iron path. And G is the total air gap length. That means total length of the iron path is the total iron path, and G is the total this gap plus this gap, total air gap length here. And A is the cross-sectional area, and mu S, I call it permeability, relative permeability of iron material. So it's definitely iron or nickel also we can have it, this sort of magnetic material. But there are few assumptions there also, because always you must have seen also experienced that magnetic flux, defining the magnetic flux in a proper manner or like this in a particular A is difficult, and there is always some error in magnetic path or like this estimation of this flux or flux density or other things there. And we often For the simplifications, we often, because we need to do right now for this crude calculations, of course, we can do use some simulation tools like COMSOL or other things there. So we have some assumptions which may not valid, but totally, but that will give you simplified the results there. One is called is uniform flux density. We know this is not possible because whenever in the air gap there would be a bulging of flux, in the corner there would be the flux density will also be different. All the things that in spite of that I assume for the sake of simplicity that because otherwise this thing will be more complicated. For the sake of simplicity, I assume that the flux density is a constant. Of course, we can also say negligible fringing because we have already assumed that the gap here is very small. This gap here is very small. That is a there. And third one is that uniform cross-sectional area. That is also not true. If it is a ring shape, we could say, but for this square shape, it is not true. But what I wanted to say is that these are only to simplify our analysis and try to get over area. So what we can say that total reluctance RT is equal to R iron loss of R air. If you recall the magnetic circuit problems, these are the two reluctance which we often bring them in series there. So what I can say is equal to L divided by mu 0 mu s into A plus of G divided by mu 0 into A, because this is due to the iron path, total iron path, armature plus is the core, and this is due to the gap mu 0 into A there. So I can say is equal to 1 by mu 0 into A, L divided by mu S plus of G. So inductance, what we can say, the nominal inductance L is equal to N square divided by R. So here it is N square into mu 0 A divided by G plus of L divided by mu S. So these are simple A there. And we can say this is equal to say K divided by G plus mu S, where K is equal to N square mu 0 into A. This is for sake of simplicity. Now suppose if G changes to G minus delta G, if G changes from, so this was our G here. If G changes to G minus delta G, so the L changes to L plus delta L. So naturally what will be? That's why the name is variable reluctance. So basically the reluctance changes, and that is the self-inductance will also change. So what we can say is that L plus of delta L. I think there is a confusion here. There could be some confusion because 2L we are using. Let us make this L as a small l. The length is a small l. Please correct it everywhere. Let this L length is a small l because we will be using inductance, capital L also. So not to confuse between this one. So you can, please do that thing here. So L divided by plus of delta L is equal to, we can say, K divided by, what is that? That is equal to okay, sorry, G plus of L by mu s. Sorry. This is G plus of L by mu s. We have it. So what we can say is that this is equal to K divided by G minus delta G plus of L by mu s. We can write it. So this one I can divide it by L and I get it 1 plus delta L by L. That means this whole expression I divide it by this L there. So what it would be is equal to G plus of L by mu s divided by G minus delta G plus L by mu. This one I will do it a little bit of simplicity, simplify this one as a, to make it, just you can do that one easily, but I am jumping 2-3 steps and to show it, delta G by G into 1 by 1 plus L divided by mu s into G. So here we are taking out G outside and I write it down is equal to, so that 1 G plus L plus mu s I am here there, into 1 divided by 1 minus delta G by G divided by 1 plus L divided by mu s into G. So what I am doing is that, just a minute. This is delta L by L. So by you just subtract 1 there, there would be a delta G terms on the top, and you take out G here, you will get it this sort of expression here. Just I think it is obvious. So what we are doing is that taking 1 on the right hand side, subtracting this one, and we can get it easily there. So the thing is that, again, we'll have to look into the nonlinearity aspect also. So what, and also the sensitivity. So what we can say, because we are trying to find out del L by L by delta G by J. In the same way, we have done it for the strain gauge for defining the sensitivity here. So we can say that del L by L is equal to del G by G into 1 by 1 plus L divided by mu s into G, and this part I can expand it in binomial series and like this, and I can write it down as is equal to 1 plus of delta G by G into 1 divided by 1 plus L divided by mu S into G plus of the other terms delta G by G into 1 divided by 1 plus L divided by mu S into G whole square plus etc. So you can see this is the area expansion there. So what we can say is that linearized, so it is obviously nonlinear. These are all contributing to the nonlinearity one. But the linearized sensitivity is equal to delta L by L divided by delta G by G. So what it is? It is equal to 1 divided by 1 divided by 1 plus mu S into G. So you can easily see that it cannot be, it is always less than 1, and this one, what we also require is that for increasing sensitivity, what we need is that L divided by mu S into G should be small, because this is the maximum what I coined it, and in that case should be mu S should be high. And that's why we normal iron material and etc., we know the permeability, relative permeability is approximately 1000 maximum or like this there. But we use some materials for this one to get it. One is ferrite core, where the permeability mu S is approximately 1000, or another new material which is called a mu metal is often used, and here permeability is much higher, it is approximately 10,000. So what we can have is that this is the area, and we can have a more, but there will be always a nonlinearity term involved. So this is the term, you can say it is contributing to first order nonlinearity and second order nonlinearity. So this things is important, because we know that as the delta G increases, nonlinearity will also increase. So for that one, normal range, we try to make it of delta L by L is approximately 10 to 20%. And because otherwise the nonlinearity will crop up. We'll again see how to use some trick to overcome the problem of the nonlinearity like this. But basically, we can say from our A itself, what we can say from our experience with the magnetic circuits and etc., that it is much easier to understand. And we'll see further how to do it. And naturally, we can also design these things there. Okay, I will stop here. I think time is up. Any question? Okay, 5 minutes time is there, 5 or 10 minutes. Any question? If it is not, I will be just, because some time is there, I would be just showing you as a there. You can think of, or there, a scheme So suppose these are the configuration. That means instead of one variable reluctance type sensor, I place two here. That means one on the top, one on the bottom there. Okay? So is there any advantage? Then this configuration is often called push-pull type. This configuration is often called as push-pull type there. Is there any advantage? Can you suggest any advantage of this one? And definitely what we can do is that, because we have to measure L1 and minus L2 or like this, then relate it with the delta G. So for that one, definitely for inductance measurement, we'll have to use some sort of AC bridge. Similar to your DC bridge, I will have to use two types of AC bridge. Say suppose I make it L1, L2, and the other things I can keep the two resistances and vary this voltage E. And obviously the unbalanced voltage is 0 there. Okay. So this L1 and L2 we can easily find out what are the values. One will be L1 is equal to mu 0 mu s n square A divided by L minus of delta G, and another will be L2 will be mu 0 mu s n square A divided by L plus delta G, small l. So because this is the amount of delta G is going, one gap decreasing and one gap increasing here. So first job I will just ask you to find out an expression of what is the value of E0 there. And the second thing is that, is there any advantage of using a push-pull mechanism for these things there? So I would like to hear from you in the next class what would be our output voltage and what is the expression for this one. If we connect it in a bridge, what would be this one, and how can we relate the output voltage with the change in the displacement, that is delta G there. And second thing is that instead of using one, if we use two which are in push-pull configuration, is there any advantage? Anything do you have in mind? Any possible reasons, at least one or two? Any possible reason for this one? What could be the reasons here? So please think of and try to find out using this formulae. Try to find out what is the value of E0 in this format and how can we design a bridge, basically, ultimately, that they design a circuit and test on their dimensions here. Okay? Any answer or any possible answer?
Sir, I'm not sure about the expression, but like, is linearity might improve.
Definitely linearity will improve, and second thing also, the sensitivity will be almost doubled up, because you can see that 1 is increasing where instead of 1 we are using 2, 1 increasing, 1 decreasing. As we have seen it for the strain gauge case also, the sensitivity will also be doubled up. Any other advantage? The third advantage, I am just telling it, you just note it down. Third advantage of number 1 is that apparently the linearity will increase, it will improve, we will show it afterwards. And second thing, the sensitivity will be doubled up, almost there. The third advantage, which is visible from this one there, had we have only one single inductance and this reluctance sensor there would have been always some force of attraction between the armature and the core there. And as a result, if we had to move it, we had to pull down or up or like this against some spring or against this, what we can say, the force of attraction. So naturally, the movement is not easy. We will have to apply a good amount of force on this one. But in this push-pull configuration, the advantage is, what is the advantage? The advantage is that in this case, both the two magnets are pulling the armature in the opposite direction. And as a result, the force of attraction gets cancelled out. And you can move this armature easily without any force. This is the third advantage. And the fourth advantage is also obvious, because the magnets are there. The magnetic core bodies are there. So, and the most thing is that this is a area, what we call it, this is armature. So external, this will provide some sort of shield for this external magnetic field here. For this external magnetic field. That means it will give you some sort of, against this, it will provide some shield against the external magnetic field. Because external magnetic field will not be able to penetrate from any side and with the armature. Anyway, those things we will be discussing afterwards, but the point is that I would like to see from you that what is the voltage and establish that the linearity improves, as well as what is the expression for the sensitivity. You try to find out there. Okay?